So here's a little question for you. What do all of these things, a speaker, a quadcopter, an Arduino, an LED, and a DC motor have in common? Well, as you can probably guess from the title of this video, they all can use something that's called pulse width modulation, or PWM for short. Now, before we jump into what PWM is and why we should appreciate it, we need to understand two types of signals. The first one is called an analog signal, and it's usually smooth and continuous, kind of like the waveform that you can see here. And it's produced by things like record players, for example. Now, the second type of signal that we need to understand are called digital signals. Digital signals are discretized, so they have two values, either on or off. These on-off states are often called high or low states, and sometimes they're represented by ones for high or 0 for low. A standard light switch is a good example of these states. If you flick it one way, the light comes on, and if you flick it the other way, the light turns off. To look at both of these signals side by side, let's think of your car's brake pedal. Now, analog control is how we brake normally, by feathering the brake as we want to come to a nice, smooth stop. Conversely, if you or your friends are bad drivers, they might use digital control over their brakes. They might fly into a stoplight and either slam it all the way to the ground, or, they might not brake at all. But here's our dilemma. We've established that with digital signals, we can only be at high or low states. So then, how can we possibly get a digital device to output a value that is somewhere in between these two states? For example, how can we get our light bulb to shine at a medium brightness when before we could only have it output either full brightness or be turned totally off? Well, to do this, we do the same things your bad driver friend does. While you might brake evenly and consistently as you approach a stoplight, your friend can get the same result by pumping the brakes fully on and then fully off of them until they reach the light. So if you pitted the two of you against each other, it wouldn't be comfortable to be in your friend's car, but in both cases, the end result is the same. You're both stopped at the light and you both stopped in the same amount of time. And this is because your average braking deceleration is the same. And this is a very important concept to understand for PWM. Now, let's take a look at what this is like specifically for electronics. So here we have an Arduino microcontroller. And guess what? These output pins, which can go to things like speakers or LEDs, can only put out either 0 volts or 5 volts. And that means we could flash our light at full brightness by cycling between 0 and 5 volts, which could be useful, but that doesn't help us out if we're trying to shine the light at a dimmed brightness that isn't the maximum light that the LED can output. Now, if we turn our light switch on, the voltage flowing through the bulb is at a maximum. This is our high state. Conversely, if we flick the light switch off, then there's no voltage flowing through the bulb, and this is our low state. Now, if we track these cycles as a function of time, we get what's called a square wave, and it's something that electronics can produce very easily, because after all, it's just turning on and off very quickly. So, if we take this square wave and we calculate the average value across an entire cycle, we get this red line, and this is our average value. Now, before we move on, let's look at three trends with this square wave. First, if we increase our max voltage, our light would be brighter and the average value of our voltage across one on-off cycle would increase as well. And second, if we increase the duty cycle, or the percentage of the time that we stay at high voltage, then our average value across a cycle would increase as well, because we're spending more time at that high state as opposed to the low state. And finally, if we sped up this whole process, you can see nothing happens to this red line. If we speed up the whole process, the average value stays the same, because after all, we're just cycling back and forth faster, but still the same percentage of our time being at these high and low voltages respectively. And before we get to put this whole picture together, let's take one more stop to speak a bit about this guy. So this is Joseph Fourier. He's the man responsible for a whole host of really cool discoveries, and in this topic we're primarily concerned with what's called the Fourier transform. So this allows us to decompose a signal in time, like a music note, into its constituent frequencies. So if we were to perform a Fourier transform of a note played at middle C, which is about 261 Hz, Then, after doing that transform, you see we get a single spike right about 261 Hertz. Now similarly, if we played a triad of 3 notes, we can use a Fourier transform to decompose them and see that we get 3 spikes at the frequencies that the tones are at. So, using these concepts, we can do a Fourier transform of the square wave that we discussed earlier to get something that looks a little bit like this. So, the leftmost spike that you can see on this axis is the average value of the square wave, which is our red line. And as we move to the right, we get these frequency spikes that decrease in magnitude. And these integer multiples of each other are called harmonics, and they can do things like introduce noise in a signal that we want. So how do we cut out these unwanted harmonics to get just the constant value term, which is the average value that we're looking for in PWM? Well, we need a filter that filters out these unwanted high frequency spikes. And the one in particular that we're talking about is called a low pass filter, because it lets low frequencies pass through unfiltered, but cuts out these high frequencies and harmonics. And the good news is that we don't need to design or buy one of these filters though. We've got one right up here. We're back at the desk with this Arduino, and now let's look at a practical application of these concepts since we've got the background information now. So here we've got 2 green LEDs. Now first things first, we'll turn them both on. And now we're going to start flashing one of these on and off. We'll begin slowly at first, and you can see that we're slowly starting to speed up and up and up. Now, this LED on the right looks like a solid color, and as you can see, the left LED came back on for reference. So when we compare these, we can see that the right LED looks a little more dim, and in reality, this right LED is flashing around 800 times a second. Now you may have 2 questions. One, why does the right LED look solid if it's actually turning on and off 800 times a second? And 2, why does it look more dim? Well, since we sped up the frequency of the light, the frequency at which we're flashing it gets pushed outside of the low pass filter that your brain is. So if you remember what the Fourier transform of a square wave looks like, all these harmonics that we detect as flashing are pushed away where we can't detect them, leaving just the average value spike on the left side. Which brings us to the answer for the next question, being why does the light on the right look more dim than the one on the left? Well, right now we're flashing the light on and off at 800 times a second, meaning that we're sending a square wave that cycles 800 times a second to the LED. Now remember the red line in our square wave? That's equal to the average value spike. Because the light is on for just as long as it is off, the average value across one of those cycles is half the brightness. So we detect the light on the right side being half as bright as the one on the left. Now, let's remember back to our discussion about square waves and the average value across a cycle, where we discussed those 3 trends. Well, if we change the duty cycle, or the percentage of the time that we spend high versus low, then we change our average value. And you guessed it, if we change the ratio of time we spend high versus low, then we can see a change in brightness of the LED. This means that using just our 2 options of max or 0 voltage, we can effectively make it look like the light is shining at different brightnesses. And if you don't believe me, here's a code snippet showing that both of these lights are set to only high or low states. And again, the reason that the LED looks solid and not flashing is because we're flashing it fast enough such that the high frequency flashing is filtered out through the low pass filter that our brain is. And this is what's so crazy about PWM. We were given something that is digital and could only be on or off, and just by changing the width of those pulses, we were able to make it, for all intents and purposes, analog for us. And this is a revolutionary concept because it allows us much more precise control over all sorts of devices. So we can do things easily like finally controlling the speed of a motor, or we could change how audio signals sound, or like you saw, we can even change the brightness of a light. We've gone and made our own digital to analog converter, or DAC for short, using just 1 bit or 1 piece of information, which are our high or low states, and that allows us to get any value in between those high and low states to mimic an analog signal, but by only using digital values. Right? So then, how does this concept relate back to all these devices here? Well, the quadcopter and the motor are similar in the sense that they both use PWM to control the speed of the motor pretty finely. And then with a light, you can use that in order to dim the brightness and set the mood just right like you saw. And then finally, you can use PWM with a speaker to change the timbre and volume of a sound. So now that I've given you a bunch of really cool ways that you can apply PWM, what have I not mentioned here that uses PWM, or what could you use it for? Let me know in the comments. But that's it for today. Pulse width modulation is everywhere and it's pretty sweet. So if you had fun, subscribe. Regardless, I'll see you in the next one.